Hi, I'm Robert Ramirez, and with me is Carlos Caldera. We're graduate student research assistants in Abel Sanchez's lab at MIT, and our research focuses on cybersecurity. In particular, our lab has been focusing on industrial control systems. An industrial control system is a bare-bones computer network that controls mechanical devices for a lot of behind-the-scenes work that society needs to function. ICS includes everything from oil and gas refineries to airplanes to power grids. The basic setup of an ICS system is shown here, and it's pretty standard, no matter what industry you're working in. The problem we studied was measuring cybersecurity risk in industrial control systems. That is, the risk of experiencing damage from a successful cyber attack. And this is a big problem because measuring risk on computer systems to begin with is still kind of an open question. How do you really do that? What are the right metrics for doing that? And for industrial control systems in particular, as opposed to traditional IT systems, measuring risk is more complicated because the way they test cybersecurity traditionally on IT networks requires things like injecting network traffic and doing other things that can disturb the system. But with ICS, you can't really disturb the system without messing up its mechanics and physical state, because maintaining that equilibrium in ICS is really important for the safety of the system and for the system to remain functional. That's what we mean by bare bones network. It's not supposed to do much. It's like the difference between a calculator and a PC. So you can't really touch ICS networks as much as you can touch IT networks. And that's where measuring the risk gets really difficult. And what that ends up meaning for people who want to measure risk for ICS systems, outsiders like us, is that you don't have as much access to the network as you would like. You might not even understand the full structure of the network. And the ICS operators might want to keep that information private. So what our lab agreed on was that we need a tool that we can give to ICS network operators that they can use themselves on their private network to determine their risk, and that they can also take and put their own data into without using an external server, so they don't have to tell us about their network. They don't have to let us touch it and mess around with it. That's the big picture. Next, we're going to talk about how we arrived at this solution and the iterations our research has gone through over the last year.
The steps that are identified for determining an ICS system's risk are shown here. These steps can be broken down to three main categories: the system identification and characterization, identifying the vulnerability and using a threat model to understand everything, and then finally calculating the risk. As you see here, these steps are a little abstract. And when it comes to actually identifying the vulnerabilities, that is in itself a very hard problem because it is actually very difficult for someone or anyone to understand exactly what they're vulnerable to without having to do some sort of field test, a pen test, or use another elaborate mechanism to determine all these attack vectors. And even then, as was mentioned before, there is no predefined metric for risk. So even if you go through all the steps and calculate your own risk, there is no defined method to compare your risk to someone else's risk. So this seems like a great 15-step process to show people that you can measure risk, but when you actually want to do something with that measurement, it's not really all that helpful. Shown here is another method for calculating the risk of a system. This is an excerpt from a paper that highlights a tool the authors built to analyze a system's risk. In this case, a library or a device. As you can see here, the tool annotates the source code to determine any attack vectors, or in this case they call them channels, and uses those channels to calculate an attack surface metric, which is used as a direct risk metric. Now, one thing we would like to highlight is that you would obviously need source code in order to run this tool, which is a great impediment to actually scaling this to any type of system, because on industrial control systems, for example, there can be a multitude of devices, somewhere up to tens of thousands, and these devices may have proprietary software which would make it hard to access the source code, or they may not be standardized, so you may have the same PLCs that all have different variations of the same source code.
With all this in mind, for our first iteration of our research, we tried to research what the best risk metric actually is. So I'm going to walk you through the thought experiment that we went through to figure this out. Imagine you have a system, a computer system, that is represented by a shape which has finite volume but infinite surface area. The surface area represents your vulnerabilities of your system. Vulnerabilities can grow without bound. CVEs keep increasing every single year. The volume of the shape represents your system. The size of your system might stay the same. Certainly, you can control the size of your system, but you can't really control the size of CVEs if you're a downstream user. So the question is, how do you account for these vulnerabilities that keep growing? A key observation here is that vulnerabilities fall into certain categories. These are CWEs. CWEs themselves map to attack patterns, abbreviated as CAPEX. In the thought experiment, you can cover an object that has finite volume with one of larger volume. This represents a mapping of CVEs to these higher level patterns. So, by dealing in terms of these higher level patterns, you should be able to cover all the vulnerabilities that you might ever experience. An extension of this idea is defense. Sure, we might have vulnerabilities, but our risk score isn't just dependent on potential vulnerabilities. It also depends on which ones we actually have. That is, which ones we haven't secured against. Security patterns are a concept in the literature that attempt to describe all the computer system paradigms necessary for preventing certain attacks. They are also finite, about 96. So the idea here was to look at the security patterns and these CAPEX and map them to each other to figure out what is theoretically covered in your system and what isn't, now and in the future. This is a representation of the 96 security patterns. It's mostly hierarchical, as you can see, so certain security patterns encompass other ones. And the lower levels of security patterns are general methods of modifying your system so that certain classes of vulnerabilities are just impossible. And this is a great idea in principle, but one problem we ran into was that even though this is a seemingly hierarchical schema, the security patterns are actually not entirely independent. Some higher level patterns defend against classes of vulnerabilities by themselves, but can prevent against others if you also implement lower level patterns. So based on this classification alone, it's difficult to tease out which security patterns are implemented in a system. At the same time, this is still ongoing research, and the authors of this research have admitted that these patterns are not totally comprehensive. Lastly, they aren't formally defined in software specifications or anything like that, but we still wanted to give it a try and map uh, what we had in terms of security patterns to the attack patterns, to these CAPEX I mentioned.
To recap, we have defense patterns and we have attack patterns, and we want to use those to develop an attack surface metric for a device. What we decided to do was to make the problem a little bit simpler for ourselves and split the surface area of a device into 4 different domains highlighted here. The software hardware domain deals with anything on the device. The architecture domain deals with all the configurations a device has, for example, the ports that are open. The network domain is comprised of anything that happens on the wire, and the organizational domain here means anything dealing with policy. Our approach was to essentially map the attack patterns and defense patterns to these domains as shown at the bottom. You have the CVEs, which map to the CWEs, that in turn map to the CAPEX. Those CAPEX then can map to a service area domain. We use this mapping from CVEs to CAPEX to give what we call an attack score for this domain. On the flip side, we would also map the security patterns that were shown previously to one of the 4 service area domains, giving us a defense score per se for the service area domain. We use our data sources to figure out appropriate attack scores from the CVEs, and for security patterns, we use a very naive metric, the ratio of how many active security patterns to how many possible security patterns for that domain. To show an example of what we were trying to do, here is a PLC that we're going to develop an attack score for. On the bottom, you have the 4 surface area domains that were previously mentioned. Now, let's go through how we develop an attack surface metric for just the software hardware domain. First, We get all the CVEs associated with this PLC and use their associated CVSS scores, essentially risk scores developed by MITRE that are assigned to each CVE, to calculate an attack score for this domain. Then, we get security patterns that are relevant to the PLC, find out which of these are actually implemented, and using the basic ratio we previously mentioned, we calculate the defense score. Finally, aggregating these two, we generate a risk score for the software hardware domain, and then we do a similar process for the other domains and develop a risk score for those separate domains. Then, if we aggregate those 4 risk scores, we generate a risk score for the entire PLC.
That sums up the first iteration of our approach, but we decided that there were some problems with this pattern approach. The main problems were that security patterns aren't well defined, and they aren't independent. Also, not all CVEs have CWEs, and not all CWEs have CAPEX. That made it difficult to generalize our system to the real world. So we pivoted, and we decided to look at general features of devices found on ICS networks. For instance, HMIs, PLCs, SISs, data historians, very standard things. We came up with a number of what we call surface area features that we determined were very common vulnerability points. We started with the question, what does an attacker want to know about your system so that they can attack you? And these device surface area features were what we came up with. Some of them are listed here. We generated synthetic data to represent a network, using some estimates of the distributions of what types of devices and configurations oil and gas networks have. We then got the CVEs associated with certain feature values, like all the Windows 10 vulnerabilities. And we used their CVSS scores to assign overall risk metrics to the network. We used CVSS scores because our prior research by Greg Falco and Carlos Caldera showed that the exploitability and impact metrics of CVSS scores are well correlated with actual risk in ICS systems, but not IT systems. The reason we pivoted away from this approach was because we felt that our distributions of these device features and device types were not that accurate, even though it gave us a great idea of how risk metrics can work. We needed to be able to look at all possible vulnerabilities associated with these particular features, which weren't totally exhaustive, and we needed to determine what the monetary system risks are and how risk propagates in a network. So we decided we needed a new way to enumerate where all these vulnerabilities come from, and that led us to attack trees.
An attack tree is essentially just a tree diagram or Bayesian belief network that itemizes all potential methods an adversary could use to reach a goal. In this case, the goal for an adversary is to open a safe. If an adversary wants to open the safe, they can do either one of these subgoals. Pick a lock, learn the combo, cut open the safe, or learn that it was installed improperly. All of the subgoals can have their own potential subgoals, and these subgoals are either independent, as in the very first layer of the subgoals, or they can be something that has to be done jointly. For example, in the very bottom here, we have that to accomplish the eavesdrop subgoal, an adversary would have to listen to a conversation and get the target to state the combo. Here is an example of an attack tree for our ICS system. In this case, the goal is a node that is in the innermost part of the network. In this example, A is the goal. Now, when we say inner, we mean that it is the farthest away from the internet. The thinking here is that an attack tree would give us a useful view of the network architecture and all the potential attack vectors an adversary would have to take in order to get to an inner node and do some actual harm. Now, with every node on this diagram, we associate a probability of exploitation, given here with the letter P. The probability is something that we can generate either synthetically using historical data or something that can be inherent to the device. Alongside that, we have an impact field, given here by the letter I. This impact field is a monetary value that is manually assigned to each node when considering it independently. It can depend on industry data or historical data.
Associate with every other device the probability and impact score specific to that node, as if the device was directly accessible via the internet. When we say accessible via the internet, we mean if this node were sitting by itself on the internet, its probability of being exploited would be p. Obviously, for nodes that are internal to a network or not directly connected to the internet, an adversary would have to go through nodes that are connected to the internet, possibly going through multiple nodes before it can reach the goal of A. So in order to represent the actual probability of exploiting, say, node B, we have to consider the probabilities of being able to exploit D and E, which are directly connected to the internet. We have two types of attackers that we can consider. First, we can consider the average hacker. So an expectation of all hackers attacking a network over time. On average, they will get to B through either D or E randomly, because we're assuming they don't know anything about the network a priori. And this is a valid way of thinking about this if you use the right data to come up with your probabilities. The data we want to use are simply historical probabilities of this type of node being attacked. It's what someone would expect to see over time if it were directly connected to the internet. And so to find the true probability of being able to successfully exploit B, we can update our belief of B's probability with the formula shown here. Alternatively, the tool we created that does all this risk calculation can also be told to assume that you're dealing with an adversary who is very skilled and knows a lot about your network, perhaps who's been doing reconnaissance for a long time. So in that case, they would be much more likely to take the path of least resistance to get to any particular goal. And so in this case, you could say that they would choose between nodes D and E based on which one has the greater probability, that is, probability of successfully attacking. They can only know this because they're experienced. Most hackers can't know these hidden probability values. And you can see this difference in the equation we use to calculate the final probability.
So we propagate these probability updates throughout the entire network to find the actual probability of the nodes being exploited based on where they are in the network. Because remember, we started with simple probabilities that are based on devices being exploited when they are directly connected to the internet, but those probabilities won't hold for nodes deep in the network. Now, given these updated probabilities, we could determine probabilistically speaking what path an adversary would likely take to go from an outside node to any inner node. In this case, we have highlighted here the path that an adversary would take to get to node A. It would start from node F and go through node C. In order to calculate the overall risk of this attack vector, we have to take into account the impacts and the probabilities of all the nodes along the path. As shown up on the top right corner, this ends up being the sum of the three elements you see there.
Now, one thing we forgot to mention is that sometimes in a network, you will have dependencies. As shown here, node E is dependent on node A being active, or not having been compromised. In this case, this is a very broad simplification, but if node A gets taken down by an adversary going through nodes F and C, then node E will also get taken down. That then means that our risk score for this path should also include the probability and impact of node E being taken down, which is shown in the top right. We use this conception for risk because it is the economic or insurance notion of risk, that risk is the expected monetary loss in a period of time. And to obtain that expected loss, you multiply the probability of such a loss event occurring by how much you would lose in such an event. So that's exactly the probability times the impact of a node being exploited. So we just sum up all those to get the risk for this particular path. And one final note in this example. Even though E is dependent on A, so that E goes down when A goes down, the attacker doesn't control E. So for dependencies, the way we model them, only the actual impacts are taken into account. The attack path itself is not extended in those cases. So with these dependencies, you actually multiply the impact of E by the probability of A being exploited.
Following the advice of oil and gas companies we've spoken to who want to understand the risks better, we've modeled 3 independent types of impact in our risk scoring tool. These different types of impact are loss of vision of a device, loss of control of a device, and loss of safety of a device. The 3 types of impact are just 3 different types of I values that are assigned to each node, and the I value is added to the total risk score when a node goes down. The type of impact we append to the risk score depends on both the type of the node that an attacker gains control over on the attack path, and it also depends on the type of node that it depends on. In this very simplistic example, the historian depends on the RTU, and the PLC depends on the HMI. So if, say, the HMI goes down, then the PLC will lose vision, and so the loss of vision impact field will be what's added to the risk score, and it will be multiplied. One last important thing to note is that our tool can assess the entropy of the risk of the system. We can simulate for each node how the compromise of that node, meaning it has a probability of 1, changes the risk of the network, or how your risk depends on one node being totally secured, meaning in this case that it has a probability of 0. This entropy metric can then be compared across networks, and for ideal security investments and network architectures to be modeled based on their monetary risk values. That is something that, as far as we're aware, hasn't been done in practice. We've made sure to build in a few different risk metrics to our tool so that a user can select the metric that is most relevant to them, and different ways of adjusting how metrics are calculated based on additional information that an ICS system operator might have. So we tried to make our tool customizable to fit clients' needs. Our code is written entirely in Python, so should be very amenable to anyone with any level of coding experience to use. You can read more about it in documentation on GitHub and the paper that we're writing.
We use historical probabilities when calculating risk, but we also use machine learning to predict future vulnerabilities. So that's why we think this is a valid approach. Thanks for watching.